So in this lecture, I'm going to briefly talk about confounding. And confounding specific to logistic regression. And so you learned about confounding in 6611 for linear regression, and a lot of the principles are the same, so we were not going to spend too much time on it. But back to confounding versus interaction. So we talked about interaction in the last lecture, and both confounding and interaction variables are variables that somehow alter the association between an exposure and an outcome of interest. And because of that, you have to take them into account. Where interaction causes the relationship between your outcome Y and your primary exposure X to vary by some other covariate, confounding, on the other hand, distorts the estimated association due to the effect of that other additional variable. So there are what are called classical criteria for confounding. And so a confounder is an extraneous variable that distorts the association that you might be interested in. Here are some examples between the exposure and the outcome. And there are 3 criteria that a variable must satisfy in order to be considered a potential confounder using the classical criteria. The first is that your exposure must be associated with the first is that your confounder must be associated with the outcome. So I'm going to let Z represent the confounder, Y represent the outcome, and X represent the exposure. So to test that the confounder is associated with the outcome, you might test Y against Z. To test if the confounder is associated with the exposure, you might test X against Z. And then the third criteria is you just want to make sure that the confounder is not an intermediate step in the causal pathway between exposure and outcome. So you want to make sure that X doesn't cause Z, which in turn causes Y. Then there are also the operational criteria for confounding. These are sort of rule of thumbs based on the changes in your estimates that allow you to call something a confounder. So in this case, we would say a covariate confounds the relationship between the disease and the exposure of interest if the estimate of the exposure effect, that is the beta for that covariate, changes when the covariate is included in the analysis. Sorry, I may have made that a little more confusing than necessary. Basically, we're interested in whether or not the beta for the main effect of interest changes when you add that additional confounding covariate. So the beta for the crude model is the one where say you have models Y equals beta 0 plus, we're going to say beta crude X, that would be your crude model. There's no covariate, there's no confounder in there. And then Y equals beta 0 plus beta crude, we'll call that beta adjusted. X plus beta 3 times your confounder. So in this case, we're really just testing whether or not adding this Z covariate is changing this beta for the X covariate. And you can look at the percent change for that, and biostatisticians and epidemiologists traditionally have different ways of defining this. And then you look at that percent change, and if there is a meaningful change, then you're going to determine that Z was a confounder. And meaningful can take on a couple different things. This is more of a rule of thumb and not like a strictly quantitative way of making a decision. But basically, if there's some clinically meaningful difference, you would want to think about that first, and often there's not. So then you could say maybe a 10% or 20% change is considered large enough to make this a confounder. And generally speaking, I'm not going to go into the details of why. So in linear regression, the operational criteria and the classical criteria agree with each other. But in logistic regression, the operational criteria and the classical criteria will not always agree. So we're going to use the operational criteria to determine if something is a confounder. So let's go through an example here of confounding. So we're back to the tetracycline and teeth discoloration example, where we're interested in whether tetracycline causes teeth discoloration, controlling for age. In this case, age is binary, it's child versus adult. We know that age does not modify the relationship between teeth discoloration and tetracycline, but is it potentially a confounding factor? Well, in this case, the crude model just has beta 1 of tetracycline, the covariate of interest, and the adjusted model adds in the covariate age as well. And we are interested in seeing whether beta 1 meaningfully changes in the adjusted model. So to run that in R, the code is printed here. First, you have to define your data. Then you define your model. Here I have the outcome as discoloration, and the crude model only has tetracycline as a covariate, whereas the adjusted model has tetracycline and age as covariates. And using that model I just calculated and the beta estimates, we get that beta hat crude is 0.42. The beta hat adjusted is 0.328. And then you can calculate the percent difference. I'm using the biostatistician criteria here, and I calculate a difference of 22%. And this is a pretty large change, so I would say this is a substantial evidence. This is enough evidence of confounding to say that we should report the adjusted relationship, which is beta hat adjusted, rather than the crude relationship. And the interpretation would be that the odds of teeth discoloration in the tetracycline group are 1.388 times the odds of discoloration in the group without tetracycline, controlling or adjusting for age.